Hi everyone! Just a brief note to let you know that we have launched a brand new podcast called Talks at Climind to interview top minds in the field of climate change to discuss on data solutions in climate mitigation, adaptation, and climate finance. Listen to our podcast to hear more from the world's leading experts from academia institute and organizations. From Climind, a team of researchers and entrepreneurs based in Cambridge, Hong Kong, and London. It's Talks at Climind, a show about the big ideas about climate change, data science, and innovation. Well, today our topic is machine learning for climate change and then manage. We're really honored to invite Dr. Priya Donti. She is joining us from Boston. Priya is the co-founder and the executive director of Climate Change AI, a nonprofit that catalyzes impactful work in the intersection of climate change and machine learning. Priya is also an incoming assistant professor at MIT of the Department of WECS, where she will be working on machine learning for power system. We'll hear more from her today, and Priya is also one of the 35 Innovators Under certified by MIT Technology Review. We also have a co-host joining us from London today, Ronnie. So Ronnie is an alumni from Imperial College London. He recently graduated from Imperial with his Ph.D. in energy and environmental engineering. Ronnie is currently a quantitative researcher at BlackRock. He also has his podcast. The topic is Talk Energy with Yes Europe. We had a long conversation with Priya and Ronnie, so this episode will be released into two separate parts. You'll be hearing the first part, and then we will release the second part soon. Enjoy. So it's a great pleasure. And then today, our topic is machine learning for climate and then energy. So we will be discussing about the really topical issues coming out from large model and then the ChatGPT and also applications of AI in energy, of course. So before we start, I just want to thank you, our audience, for paying attention to Talks at Climind. So Talks at Climind is trying to curate the conversations of data science and then the really important discussion on climate change adaptation and mitigation. So without further ado, we will bring in our speaker today. So first of all, we will start with Dr. Priya. So Priya, can you say hi and then share with our audience a little bit about where you're coming from and what you're working on?
Absolutely. Thanks, Karen, for having me today. So as Karen mentioned, I'm Priya Donti. I'm a co-founder and executive director of Climate Change AI. And we're a global nonprofit that aims to foster impactful work at the intersection of climate change and machine learning. And we do this by bringing together people from machine learning and data science backgrounds with those from climate change related backgrounds to form teams, collaborate, do impactful work together. And we provide the kind of education, funding and other infrastructure necessary to make those collaborations fruitful. And in addition to that, I, as Karen mentioned, I'm an incoming assistant professor at MIT EECS. And my research focuses on methods for forecasting, optimization, and control in power grids. Specifically, what a lot of my research thinks about is as we start to deploy, data-driven methods like machine learning on power grids, because we need to manage grids at better speed, scale, and precision. How do we do this in a way that still satisfies and sort of respects all of the physics that we face on the power grid, because we don't respect those physics that can lead to power grid outages. So my work thinks about how do you actually embed that physical knowledge within the design of machine learning methods. So that's me.
Thank you so much, Priya. We have a lot of questions, but before jumping to those, we want to hear from Ronnie as well.
Yeah, of course. Thank you very much. I'm currently a quantitative researcher at a investment company, BlackRock. But just a clarification, nothing of what I say today is BlackRock related. So I'm not representing the company at all. And prior to that, I was a PhD graduate from Imperial College London, working on using machine learning and optimization to decarbonize industrial sectors. And also in the meantime, I used to be a host for energy-related podcast, Talk Energy with Yes Europe, where I was serving as the board member for the youth organization for energy professionals in Europe. So we're looking forward to the discussion today.
Thank you both. So before, I think it's important to define the scope because we have a lot of buzzword of AI and technology, especially today. So my first question to Priya, can you help us to kind of define the scope about what kind of key areas you're defining when we're talking about the energy or grid system you're working on?
Yeah, okay. So maybe there are a couple of concepts here, right? There's AI, power grids, climate change. So maybe let's talk briefly about the scope of each of these. So when it comes to AI, right? AI refers to any algorithm that can perform a complex task, and often one that is associated with human intelligence. So things like speech, perception, reasoning, things like that. And machine learning refers to any method within that kind of learns automatically from large amounts of data. So when I think about the machine learning in my work, this paradigm of learning from large amounts of data can play out in a lot of different ways, from kind of forecasting to providing controllers via reinforcement learning to many other kinds of things. When it comes to energy systems, of course, refer to a combination of power systems, natural gas systems, heating systems, all of the different systems that are bringing us energy. My specific research focuses on power grids specifically, thinking both about how we kind of more centrally optimize power grids and how we optimize power grids in a more distributed manner. So my research covers all of that. And on the climate change side, of course, climate change affects virtually every single sector of society, and we have to both mitigate greenhouse gas emissions and adapt to the effects of climate change across all of these sectors, be it power systems, buildings, industry, disaster response, many, many different things. And so climate change AI's work actually, convenes people across all of these different areas in order to use machine learning and data science to address climate change related challenges across these different sectors.
Yeah, thank you. And just to add on that, when we mentioned about climate change AI, this is a nonprofit started a couple of years ago, and then now it has been growing. I believe one of the largest community with the practitioner and the researchers in the group. And then you actually have an amazing directory of people like listing down the profiles, and I really encourage audience to look into. So in our previous episode, we interviewed Breakthrough Energy. I think they're working on something really relevant, is to build this open source energy system and also database, and they're simulating potentially a new grid system in the States. So I want to hear from your perspective about like how, when we're talking about the simulating new grid system or AI application, how this is different from traditional statistic approach or optimization, if that can be called like computational research.
Absolutely, yeah. So like I said, machine learning can be used in a wide variety of ways. So kind of forecasting and estimation, as well as actual optimization and control. So in the forecasting and estimation space, historically, there have been, various kinds of heuristic methods that have been used. So things like if you're trying to forecast electricity demand, some rules where you can write down, is this a weekend or a weekday? Is there a holiday today? What did the demand look like yesterday? And system operators used to specify kind of a set of rules from which they would derive some kind of demand forecast. Methods from machine learning and statistics, right? They kind of instead really look more deeply at the data and try to identify correlations among the data that can then be kind of used to create a forecast now. So I would say that honestly, in the kind of forecasting space, machine learning and statistics are used kind of very similarly, and both of them are fundamentally trying to learn trends from data in order to come up with more precise forecasts rather than rule-based systems, which is what existed on the system before. Now, in the kind of optimization and control realm, you have, for example, on the control side, traditional methods from control theory, where you write down some specification of the dynamics of your underlying system. You make some simplifying assumptions about what your controller can look like, the functional form of your controller. And then you write down a set of equations to try to actually solve for a controller that satisfies certain criteria on your system. And so whereas machine learning methods really are much more about trial and error in a way, trying to actually look at the data on the system and learn how to do something data-driven and nuanced. And the kind of interesting thing about this is the control theoretic way, where you write down a set of equations and solve it. You get various kinds of guarantees by doing that, but because you have to make so many simplifying assumptions to make that work, you tend to have controllers that are less performant or less precise in managing the grid compared to what could be done. Whereas machine learning methods, which learn by trial and error, they can learn to do things that are very nuanced and high performing, but they're not good at satisfying the assumptions in physics and all of the stability requirements, all of those kinds of things that need to be satisfied on the power grid. So actually what some of my work does is try to bring these two things together. How do we kind of embed some of our knowledge from traditional optimization and control into the way that we design machine learning methods, so that we have some mix of data-driven learning plus provable guarantees.
Can I just ask one follow-up question on that point? So you mentioned about the additional benefits that machine learning statistically can bring to the traditional optimization. In the power grid specifically, where do you see, where does that spike of additional benefit would come from? Is that
right. Yeah. So I would say on the forecasting side, these methods can kind of combine like a very heterogeneous set of data. So things like combine historical information coming in from sensors, combine video feeds that are telling us how clouds are moving overhead of a site where solar panels are. So I think this just sort of bringing together many different types of data and being able to ingest it and find correlations between it and really come up with insight from it is where machine learning shines on the forecasting side. On the optimization side, so thinking about optimization problems like AC optimal power flow, unit commitment, market clearing algorithms that power system operators use. The kind of traditional, fully physically correct model there is very expensive to solve. And so power system operators often use heuristics. So for example, they make linear approximations to the physics of the underlying power grid through things like DC power flow in order to solve these problems. But the challenge is that then as we start to have more solar, wind, and other non-spinning generators on the power grid, we kind of decrease what is called the system's inertia. So basically like the buffer that we have to imprecisions that might happen in the control of the grid. And so these physical approximations like DC power flow that power system operators traditionally use are starting to cause some problems. So where machine learning can come in there is it can try to provide approximations to kind of a different kind of approximation to the true physics of the system. So some of my work looks at how do we look at this problem of AC optimal power flow, which really captures the true physics of the grid in this centralized optimization, and use machine learning to approximate it in a way such that you keep fidelity to the true physics, but that you kind of speed up the solution of the AC optimal power flow problem as a whole. And the hypothesis is basically that having an approximation of the true physical model rather than using a cheaper physical model is a better thing to do for a power grid. So those are some examples, I think, of where machine learning can shine. And then when it comes to distributed control, I think when you just have a lot of different devices that are trying to control many different things on the power grid, leveraging the sensor data that's available rather than making assumptions about our system that might not be substantiated by the data can definitely have a lot of benefits.
Yeah, you already answered the next question I want to ask. But this is another key point I want to bring down to hear from your thoughts. I think the climate is a complex system, and same as energy. As we are introducing new sort of energy supply, and during this transition, it's a puzzle. We really do not have the experience to talk about before. So which means making simulation a critical part to trying to understand what can happen before we actually build it. So my question is what kind of additional challenges you can see, especially in this energy transition area, especially in area like emerging countries, which doesn't necessarily have the infrastructure as most of the developed country have, and then how, like, if any, this kind of disproportional impact in emerging countries, like machine learning, can potentially play a role, and your feedback on that. Yeah.
Absolutely, yeah. So, of course, like the energy transition in emerging countries involves a combination of kind of often improving the reliability of power. Of course, many places that are connected to the grid don't have 24/7 access to power. It's not reliable when it's there. And then also energy access, right? Making sure that people do have access to energy in places where they don't. Machine learning can play a role in these kinds of things. So I have talked a bit about how machine learning can help with, optimization and control of grids, the kinds of things I was saying in developed contexts there, roughly generalized to developing contexts, where the goal is to really take advantage of the data that's available on the system alongside any physical knowledge we have to try to just provide better ways to control and improve reliability and stuff like that. And in terms of energy access, there is some work going on to try to, for example, predict what the latent electricity demand might be. So if a grid were to be extended somewhere, what was the amount of demand that it would likely be serving? And how do you use that to actually plan the grid out in the first place? So for example, my colleague, Simone Phoebe, who did her PhD at Columbia and now is at Microsoft, she has done a lot of work in this area to try to use a combination of satellite imagery and other on-the-ground data to try to predict what the latent demand will be in order to inform planning efforts.
Yeah, and then just to continue with that, about data. So from climate point of view, we're working on the climate data, trying to find the connections of different sort of information so we can use better use of. So the question is about what you think, is there a data challenge regarding like availability or in the duration, like how you process in your research work, or the way like currently data has been used. And then this goes back to just mention our last episode for energy issues. Our previous speaker mentioned for many situations, it's really hard to get the detailed granularity level of consumption data, so which we have to use synthetic data to run the model. So I want to hear from like your views on the challenge of data side.
Absolutely, yeah. I mean, I think there are several kinds of data challenges that come up in the power grid space. So some of it is availability. So for example, in the US, power system operators do provide various kinds of market data, but if you do want something more granular, it tends to be potentially not collected, potentially secret, or potentially only available to people who are participants in that actual market. And then you also have the issue that, there are many, many contexts and countries where that data, even in that form, is not available. And so the question of, where are we actually, where do we have data to actually develop innovations on top of is not a kind of uniform answer across the globe. In addition, I would say that on power grids, so I think when people think about sort of data availability and data gaps in a lot of other areas, they think about, well, the goal is to estimate something, or the goal is to really understand what a system looks like. But in power grids, we're also thinking about, how do you not just understand the system, how do you actually optimize and control it? And that leads to kind of a whole other set of challenges, which is not just static data, but dynamic simulation and the ability to try out things on simulation. And so I would say the availability of good test beds and simulators is low. And this has to do with both, the granularity of data available to feed into them, but also some knowledge about just what does the physical power grid actually look like at a detailed scale, and can that information be released publicly? And then access. Again, there are some simulation environments and test beds, but they're not kind of widely accessible or easily downloadable to anybody who wants to do this kind of research necessarily. There are some IEEE test cases and more advanced test cases that actually give you something about the topology of the power grid that are out there, but they're all synthetic grids and there are not that many compared to kind of the multiple things you might see on a real grid. So in addition to sort of data availability and granularity, I would say also simulation availability is also a bottleneck at the moment.
Maybe, maybe just another quick follow-up question on that side. Suppose, ideal world where we have access to all kinds of data, granular, well screened, well cleaned. What's the most exciting research topic or that can be commercialized or anything in the field of power grids?
Yeah, I mean, I would say that again, this idea of how do you come up with dynamic and distributed controllers for the power grid in order to provide necessary flexibility to enable the integration of renewables. I think this is just generally like a very interesting and important area. But again, like data alone won't solve that, right? So simulation and such is needed, but then also pathways to deployment. So if I had perfect data and a perfect simulator today, I could probably test out all sorts of methods to try to dynamically manage a power grid with lots of renewables. But then the next question is, how do I actually deploy that, right? So because right now, a lot of power system software is provided by a small number of entities. It's centralized, it's not open source, and sort of coming up with your own full power system suite to sell it to a system operator is not necessarily within the scope of what a lot of, for example, academic groups can do unless they decide to build their own company and try to compete in that space. And so I would say that I think there's a lot of exciting stuff that can be done to provide just more dynamic data-driven optimization control to better integrate renewables, provide flexibility to the grid, all of that sort of thing. But even if we did perfectly from a research perspective on that front, I think there are still a couple of steps to actually make that deployable today.
Yeah, I totally agree. And I think like the debate of whether we should open source data, open that level of access to a general public, not just depending on what kind of research topic is important. Like sometimes we need to consider the policy, especially power grid is operated in a special way in different countries. And what is, I think, make the climate issues really a trilemma. Like sometimes we need to consider the security, sustainability, but also affordability. Thank you so much for joining our episode, the first part, conversation with Priya and Ronnie. You'll be hearing the second part in our next episode. See you next time.